Hello, welcome to my presentation. My name is Michał Włodarczyk, and I will talk about vertex deletion parameterized by elimination distance and even less. This is a joint work with Bart Jansen and Jari de Kroon. I will be talking about parameterized algorithms for vertex deletion problems. I will start with an exemplary problem to give some context. This problem is odd cycle transversal, in which we want to find the smallest set of vertices to hit all the odd cycles in the graph, or equivalently, whose removal makes the graph bipartite. When talking about parameterized algorithms, we first need to choose parameterization. One common choice is to consider a parameter being the solution size. So we are interested in algorithms with the running time of the form some function of k times poly n, and we want to detect solutions of size at most k. Other common choice of parameterization is to use some graph measure as tree width or tree depth. Tree width is upper bounded by tree depth, but on the other hand, tree depth can sometimes lead to polynomial space computations. However, the first two parameters, the solution size and tree width, are incomparable. One can find graphs with small tree width but large solution size, and vice versa. This leads to a question: can we combine the techniques used in these different parameterized algorithms to find a larger class of tractable instances? So we are interested in some new parameterization, which can be arbitrarily smaller than both solution size and tree width, but under which the problem would remain FPT. So let me introduce the parameters. First, tree depth. Consider an process in which in each round we can remove one vertex from each connected component of a graph. And the minimal number of rounds to remove all the vertices is the tree depth of the graph. This is captured by the following recursive formula. Equivalently, tree depth can be seen as the minimal depth of an elimination forest, which is a forest where each node corresponds to a vertex of a graph, and adjacent vertices correspond to nodes which are in ancestor-descendant relation. And now we want to make this construction aware of some graph class H. For example, let H be a class of bipartite graphs. So we modified this definition only in this point. So we treat the graphs belonging to class H as simple. And the rest of the recursive definition stays the same. And this gives us the H elimination distance of a graph G. Similarly as before, we can treat this parameter as the minimal depth of an H elimination forest. This is a concept similar to an elimination forest, but here a leaf can represent some arbitrarily large component which is bipartite, or in general belongs to the target class H. Observe that H elimination distance is upper bounded by the deletion number to H, so the minimal number of vertex deletions to make the graph belong to H. And this is just because that in H elimination forest, all the white vertices must form an H deletion set. So now let us recall the definition of a tree decomposition. This is a decomposition of a graph. G is it is a tree of backs, and each vertex of G must appear in a connected subtree of T, and each pair of vertices adjacent in G must meet at some bag. The width of a tree decomposition is the maximal size of a bag -1, and a tree width of G is the minimal width of a tree decomposition. So the simplest idea to make this concept aware of some graph class H is to allow arbitrarily large bags, some special bags, as long as they induce subgraphs from the target class H, and each special bag is adjacent to only one regular bag. And the remaining conditions of a regular tree decomposition should be satisfied. So a width of such a 3H decomposition is the maximal size of a regular bag, -1. And we define H3 width as the minimal width of a 3H decomposition of a graph. Now let me give some intuition why this kind of decompositions still makes it easy to solve the problem. So recall the classic dynamic programming algorithm to solve odd cycle transversal when given a tree decomposition. So this is a bottom-up dynamic programming routine in which for each bag we consider a family of states where each state specifies which vertices are to be deleted by the solution and which vertices are going to be left in our final bipartite graph and which are going to be on the right. And for each state, we want to compute the minimal number of deletions to make the subgraph induced by such a subtree bipartite and to be consistent with the state. And here we only need to check if such a partition is valid, so there are no edges like that, and to collect information from the children nodes. So when we consider a 3H decomposition, where H is the class of bipartite graphs, and we want to make this dynamic programming work on this more general decomposition, we only need to consider one more case. A case where we have a regular bag and its only children is a special bag. So in order to fill the dynamic programming table, we need to solve the following subproblem. So we ask for the minimal number of vertex deletions here in this large bag. So the obtained bipartite graph has the orange vertices on the left and the blue vertices on the right. And since we are guaranteed that this graph is bipartite, this is exactly the same subproblem one comes across when solving odd cycle transversal via iterative compression. And this subproblem turns out to be solvable in polynomial time. Let me give some quick summary of these parameters. So for hereditary class of graphs H, we define H3 width and H elimination distance. And H3 width is upper bounded by both tree width and the deletion number to the class H. And in general, both these parameters can be large, while H3 width can be very small. And similarly, H elimination distance is upper bounded by tree depth and deletion number to H. Similarly, as with tree depth and tree width, H3 width is upper bounded by H elimination distance. And the last interesting property is that when the tree width in a class H is bounded, then any 3H decomposition can be transformed into a tree decomposition of a comparable width. So this parameterization by H3 width is only interesting for classes of unbounded tree width. So we are not interested in, say, trees or outer planar graphs, but rather bipartite graphs, chordal graphs, planar graphs, or graphs of bounded degree, and so on. We can consider this problem for any hereditary graph class H, and similarly as we defined odd cycle transversal, in such a problem we ask for a smallest set of vertices whose removal makes the graph belong to the class H. And our goal is to solve H deletion parameterized by H triwidth or H elimination distance, which would give stronger parameterization by than the parameterizations known so far. And here we arrive at some problem. While it is easy to define some graph decompositions that makes it easy to solve H deletion, it may be the case that finding such a decomposition is a harder task than solving H deletion itself. We would like, when the graph has small H triwidth, for example, we would like to be able to compute some 3H decomposition to be able to run the dynamic programming routine. So while computing triwidth or 3-depths is FPT, it is unclear for some class H whether computing H triwidth is even XP. And there is a recent line of research focusing on just computing these parameters, and we have results for H being, for example, class forbidding some minors, forbidding some induced subgraphs, or class of bounded rank. But all these results rely on some algorithmic meta theorems, which makes the running times huge. So we take an alternative approach. So we don't have to compute the composition of optimal width, but when we are promised that the H triwidth is bounded by K, it would be okay to just find a 3H decomposition of width H of K, where H is some function. This would, of course, make the dynamic programming routine run in a slightly worse running time, but the bottleneck is just to compute a decomposition. So I'm now ready to present our main contribution. So this is a theorem that when H is a graph class given by either a finite number of forbidden minors or topological minors or induced subgraphs, or H can be a class of bipartite, chordal, or interval graphs, then there is an FPT algorithm that computes an approximately optimal 3H decomposition, and this approximation guarantee is polynomial with respect to H triwidth. And the same holds when we want to compute H elimination forest. These running times and approximation guarantees vary over different graph classes, and now I will just present how this theorem looks like for bipartite graphs. So there are three algorithms, and first takes a graph of bounded H elimination distance, runs in polynomial time and space, and returns an H elimination forest of depth roughly cubic in K. It is important that the algorithm runs in the polynomial space because computation with H elimination distance can lead to polynomial space algorithms, similarly as parameterization by 3-depth. In worse running time, we can get a slightly better approximation ratio. And also for H3 width, there is a similar algorithm with a cubic approximation guarantee. So now I will quickly sketch how to compute this approximately optimal decompositions. So suppose we are given a graph of small H3 width, so it admits some unknown 3H decomposition. And suppose we are given a vertex and promised that this vertex belongs to some special large bag. So now we want to find some good candidate for this bag. And it means that we are looking for some vertex set which contains V that induces a subgraph belonging to the class H and whose neighborhood is small because its neighborhood is contained in just one regular bag. So we can define such a structure and call it an HK separation, which is a pair of disjoint vertex sets CS, such that C induces a subgraph belonging to class H. Its neighborhood is contained in S, and the size of S is moderate. And we consider a problem of finding such separations where we are given a vertex V and we want to find the separation that would cover the vertex V. So V should belong to the set C. And we again settle for approximation. So we are, when such an HK separation exists, we are happy just to return an separation where the size of S is bounded by some function of K. So how this helps us in constructing a decomposition? We use the separation finding subroutine iteratively to partition the graph into connected vertex sets such that each large bag should be contained in one of these sets. So now we contract all these sets and obtain a new graph G prime. And because of this property, we can prove that the 3 width of G prime is bounded by H3 width of G. So now we can use the known algorithms to compute a 3 decomposition of G prime and then turn it back into a 3H decomposition of G using some properties of the HK separations. And the same outline works for finding H elimination forests. Sticking to the example of bipartite graphs, I will quickly sketch how can we solve such a separation finding problem, and recall that we have a vertex V and we are looking for a set C that would induce a bipartite graph and would have some small neighborhood. And we construct an auxiliary graph G prime in which each vertex V gets 2 copies, V prime and V double prime, and each edge UV translates into 2 edges, U prime V double prime, U double prime V prime. And there is an observation that graph G is bipartite if and only if every vertex in G prime is disconnected from its copy. And this observation implies that once we have some CS separation, then when we take both copies of each vertex in S, then this forms a V prime, V double prime separator in G prime of size at most 2K. So now we can just find a minimal V prime, V double prime separator in polynomial time, and this can be transformed into H2K separation covering V in the graph G. So this provides us with a 2 approximation for separation finding problem. And for bipartite graphs, this procedure works in polynomial time. But for other graph classes, we present FPT algorithms based on some branching rules using important separators and some other properties such as Erdős-Pósa property. To summarize, for each of considered class H, we present an FPT algorithm to solve separation finding with polynomial approximation guarantee, and we show that this implies approximate algorithms for computing 3H decomposition and H elimination forest. So the hardest part of the task here is done. Next, to finish our quest, we would also like some meta theorem that would allow us to solve H deletion when this 3H decomposition is done. And we give such a meta theorem. Namely, if class H is closed under taking disjoint union of graphs, and it enjoys something called the finite state property, and furthermore, suppose that H deletion is FPT parameterized by the solution size, while some vertices are marked as undeletable, then when all these assumptions are satisfied, then we can solve H deletion parameterized by the width of the given decomposition. And most of the considered classes satisfy these 3 conditions. One counterexample is a class that excludes a disconnected minor or a disconnected subgraph. So we give an example of such a class that is not closed under taking disjoint union of graphs, and this theorem doesn't work. And furthermore, then H deletion becomes NP-hard already when the value of H3 width is constant. Towards about some other results. So parameterization by H elimination distance leads to polynomial space computation in some cases. And also we can consider some other problems instead of H deletion parameterized by H3 width, namely vertex cover turns out FPT parameterized by H3 width when H is a class in which vertex cover is polynomial time solvable. So if you are interested in concrete running times and approximation guarantees for various graph classes, please check the paper. And there are also a lot of open problems around to extend this budding theory of hybrid parameterizations. I hope you enjoyed this video and thank you for listening.